So, hello folks, so welcome to lecture 51. So, I think the stage is now set to actually see dissipative property and the conservative property as the same side of the coin. The dissipative property knows everything about the conservative property and vice versa, but through the dynamics, right. So we will actually try to see how that is the case probably by the end of today's lecture. So that's where we ended the last lecture, right. So we said that there is the imaginary part of any thermodynamic property, which is the dissipative part, the real part, which is the energy storage part, and I ended by saying they are actually married to each other, right. So they know everything about each other, but through dynamics, right. So dissipative part would have certain dynamics, imaginary part has the conservative part has certain dynamics, and these dynamics are related in the frequency space, right. So we'll actually try to see how that is the case, but before that let us actually look at so for example I have P of omega, right. So I said that is equal to chi of omega times E of omega, right. So this is how I wrote a linear property in the omega space, correct. Then G of omega as a result is equal to so G of omega is the effect, right, and f of omega, I said this, I rewrote it as f of omega is the forcing function and r of omega is the response function. Okay. Okay. Now let us look at, so this is in the frequency domain, right. So from frequency domain, if I go to time domain and I want to see how this g of t is changing in time, right. So you remember earlier we have come from when I was looking at the relaxation, I came from time domain signals to frequency domain signals by doing what is called Fourier transform, right. So now I have to do an inverse Fourier transform of this, right. So to go from time domain to from frequency domain to time domain. So I do what is called inverse Fourier transform. Okay. Now so this actually looks at minus infinity to infinity r of so okay, before I move on, so we may want to observe that a Fourier transform of a product, right, or inverse Fourier transform of a product is nothing but convolution, right. So it's a convolution operation. So it's r of t convolved with f of t. Now what is convolution? Convolution is this operation where I have I think we did a bit of convolution when we were doing lattices, right. So convolution is so I do this from 0 to so 0 to infinity, r of t minus tau f of tau d tau, right. So this is the convolution operation. We studied convolution a bit in the earlier part of the course when we were actually looking at the lattice, the motif, lattice convolved with motif actually gives the crystal structure, right. So in that context we have studied convolution, right. We will come back to this, right. So the time, so the property in time is not really a multiplication of r and f, right. It actually so looks at the change of f as a function of time until time t, right. So this is until time t, okay, not right. So the change of f, so how is f evolving with time, right, all the way from 0 to t, all the so f evolves from 0 to t, right. So in a certain way, so it takes all the history into consideration, and so at every time it is actually multiplying it with a response function and integrating over it, right. So this takes into account the g of t, right. So has information about the history of the signal. F of t, okay. So from 0 to t, okay, that is point number 1. And point number 2, so what I mean to say is that this property r of t minus tau, you have to multiply it with f of tau. So you have to modulate f of tau with r so as to give g of t, right. So, f of t is modulated or weighted, right. So, I have to always weigh my f of t with r of t minus tau, weighted with the response function to give the g of t, right. So, first of all f of it is not just f of t, okay. So, f of tau, let us say where is weighted with the response function r of t minus tau, right. So, so in some sense so for, and this happens for all tau, right. So, for all tau less than t, okay. So, this is a very complex way of understanding property. It's some sort of modulation, this property at every time instant, right. So, at time t equal to 0, time t equal to t1, t2, t3, all the way up to time t equal to t, I look at so the f of tau, modulate it with the property at that time, property is also changing with time, right, at that time, and then multiply that, add it with time next time t2 for property times the f of t, plus add it, and so on and so forth, and that is how I am building a map of the history, and all this is given as g of t, right. So, it sounds a bit complicated, it is a convolution operation. So, mathematically all this is just called convolution, right. So, in time domain so convolution actually describes what my response functions are or what my properties are, right. So, it is not simply r of t times f of t, but r of t convolved with f of t, okay. So, that is something that I want you to pay attention to. In frequency domain it is just a multiplication, g of omega equal to r of omega times f of omega, okay. All right, good. So, now we are going to use something in the time domain, right. So, but before that let us actually look at one of the properties that we have been ignoring. We said that this course is electrical so materials designed for electronic, electromechanical and optical properties, right. And one of the most important optical properties is not second harmonic generation, because we have looked at second harmonic generation, rather it is refractive index, right. So, n, okay. Now, n is also a thermodynamic property, and in fact if you look at Maxwell's equations, n turns out to be square root of epsilon omega epsilon mu, where epsilon is epsilon r mu r, where epsilon is my dielectric constant and mu r is my magnetic permeability, right. Now, for non-magnetic materials where mu r equal to 1, n is just square root of epsilon r, or epsilon r is n square, right. So, in some sense if I talk about n, I talk about epsilon r, or if I talk about epsilon r, I talk about n. So, refractive index and dielectric constant, especially at visible light frequencies, right. So, they have similar information, right. So, but so refractive index is something which is more often used, right. So, than the dielectric constant at visible frequencies, okay. So, that is why I did not pay special attention to n, but now the time has come to pay special attention to n, okay. So, now n is also a property, right. So, of the material. So, n also this is a thermodynamic property. So, n also will be having a real part and n has an imaginary part, right, and both of them are dependent on frequency omega, correct. Okay, so that is good. Then if I, so what is n doing really? So, if I have so n slows down the velocity of light in my material, right. So, if I shine light at a velocity c on a material with a refractive index n, right. So, the velocity of light here will be c by n. So, as a result it also changes the phase of the light that passes through the material, okay. So, the velocity changes, by a factor of n. So, essentially it becomes c by n, okay. Okay, so that is good. Now, so what is, so let's look at this problem. So, the incident wave in my material is given as, so this is a solution for wave. So, e power I k x minus omega t, okay, where k or k vacuum, right. So, where k is at k vacuum is actually equal to 2 pi by lambda in vacuum, okay. So, that's, this is a wave, right. So, a wave propagates in space and in time, right. So this is a simplest equation of what is called a plane wave, right. So plane wave has all these phase fronts that are propagating in this fashion, and all these phase fronts are given as kx minus omega t is some sort of a constant. Okay. So okay, now in the material, and there is some amplitude, right. So I am ignoring the amplitude. Okay. So in the material, this wave, right. So the what is the velocity of this wave? Velocity equal to omega by k, and that in vacuum is c, right. Now in the material, right. So if I actually so I am going to take out the omega, right. So e power I omega x by c minus t, right. So this is the velocity of wave in vacuum, right. So in material, my c becomes actually c by n, right. So this is not yet in material, this is still in vacuum. C goes to c by n, right. So the wave actually, the plane wave propagates as in the material e power I omega x by c by n, right, minus t. Okay. All right. So and so omega by c I know from here, right. So let us see, so where is lambda? Omega by, okay. So let's get back to that, but that is equal to e power I omega x by c times, this time n is a complex number, n r plus I n I, okay, times e power minus I omega t, right. So this is how I am going to write it. Omega by c, right, is so I said in vacuum, I said omega by k equal to c, right, or omega by c equal to k, or that is equal to 2 pi by lambda, but lambda in vacuum is equal to 2 pi by lambda in vacuum. Okay. So I am going to write this expression again as e power I 2 pi by lambda in vacuum, which is the light wavelength, that is 500 nanometers or whatever it is, times n x, right. So times nr plus I n I, right, times e power minus I omega t. E power minus I omega t is the time fluctuation. I will so that always carries, so let me not worry too much about that, right, and that is equal to e power minus I 2 pi nr by lambda vacuum, right. So x times e power minus 2 pi by lambda vacuum times Ni, right. Okay. And so there is a propagation, there is a time propagation which is e power minus I omega t, right. Okay. Now if I have something like this is sinusoidal, this is just exponential, right. So how would this wave look like in space? In space, right. So if I have x, this is x, this wave is oscillating, all right, good, but it is reducing in amplitude, and this reduction in amplitude is given as my e power minus 2 pi Ni by lambda times x, right. So this is the wave is actually modulated by an absorption, right. So it is actually reducing in amplitude, right. If it is reducing in amplitude, it means that the material is absorbing light. It is absorbing light and doing something else that we will worry about later, but it is absorbing energy from light, right. So if I so there is something called, if I shine light at an intensity I on my material, right, I naught on my material, and the material has an absorption alpha, material is going to attenuate the light, right. So, the I that comes out of this material will be I equal to I naught times e power minus alpha times t or x. Okay. So, this alpha is what is called the absorption coefficient. This is my material, and the light that comes out here will be I naught e power minus alpha times x or t. Okay. If this is x, this is x, right. Alright. So, now I am saying my so what is the intensity of light that comes out? Intensity of light that comes out is so here. So, if I look at this wave, right. So, this wave is the amplitude of light, and if I look at the intensity of light, this times I naught, right. So, this times some a naught, right. If I look at the intensity will be of so wave 1, intensity of wave 1 will be I equal to a naught square times so if I square this, that will be 1, if I square this, that will be 1. So, the only thing I have is e power minus 4 pi Ni by lambda times x. Okay. So, now if I compare this, I should be, which is equal to I naught e power minus alpha x. So, alpha, my absorption, equal to 4 pi imaginary part of refractive index by lambda, right. So, this is a simple equation for absorption coefficient. This is called absorption coefficient, and this one here is what is called the extinction coefficient. They are related, right. So, so alpha is again dependent on omega, Ni is dependent on omega, and so alpha equal to 4 pi Ni by lambda, this is in free space or lambda in vacuum. Okay. So, alpha equal to 4 pi by lambda, this is a constant times Ni omega. Okay. So, whether I talk about extinction coefficient or whether I talk about absorption coefficient, I am actually talking about absorption of light in a material, right. So, that is given as imaginary part of Ni, that is the extinction, and that is actually related to the absorption, right. So, this is the absorption coefficient. These are one and the same. Okay. So, I mean they are related by just a factor which is 4 pi by lambda. Okay. So, whether I talk about extinction, which is the imaginary part of refractive index, hence, right. So, the imaginary part of refractive index tells me about, it is called extinction coefficient, and it tells me how much light will be absorbed, right. So, it is that is the dissipative nature of refractive index, right. So, or dissipative nature of refractive index is the absorption of light by the material. Tells me, that is Ni, tells me the absorption of light in my material. Okay. All right. So, with that, let us come to a very important exercise, right. So, now all right. So, let us say I have some electric pulse, right, that I shown on my material. So, in some sense I am going to use electric field in light, right. So, any form of electric field in light is an electric pulse, right. So, in the sense that when I say electric field, it can be measured electrically or it can be optical also in nature, because everything is the same electromagnetic wave, right. So, I sort of say I shine electric field on my light on my material, means I can just apply an electric field, a DC electric field, that is also okay. 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 So, this I shine on my material, right. So, now this is the time domain, right. So, what is the frequency domain response of this? This is in time. If I look at the frequency domain response, the frequency domain response of a function which is a step function like this is actually some sort of a Bessel function, right. So, this is like a slit, right. So, in a slit you do diffraction experiment, and the frequency response. So, E of omega as a function of omega, if I look at it. Now, that is going to be something like so it is, sorry, let me not draw omega E here, let us draw E here. So, that peaks about some omega naught, and I have a response which is going to be like this, right. So, it's a sinc function or a Bessel function, or so in 2 dimensions it's a Bessel function, in 1 dimension it's a sinc function, and so on and so forth. So that is easy to derive actually. Okay, all right, good. Now, I am shining this on a material. So, I shine light E omega on my material, right, or in other words that also has a time dependence. E of t is the time dependence, corresponding time dependence. And very importantly, the material absorbs a frequency, right. So, my material has absorption because of some sort of band transitions. We will actually look at that in the next class, right. So, at omega naught, some frequency omega naught, right. So, material absorbs at, let us say, some frequency which is this. So, this is my hypothetical material which is absorbing, this frequency gets absorbed, right. So, then I have to subtract from this, right. So, this is the absorption. So, in the frequency domain I am going to subtract from this a signal with this is the absorbed this thing, right. So, that is only at this frequency, it is sort of a delta function there, right. So, I am going to subtract this, right. So, if I subtract this, now what is this signal in time domain? This signal in time domain, E absorbed in time domain, which I have to subtract, is it's just a sinusoidal function, right. So, it has only a unique frequency, and so the inverse Fourier transform of this is just a sinusoidal function. Okay, all right. So, now what do I detect, right? So, I am detecting in time domain, right. So, this is the input, or this is what I shine into the material, this is the input. This is what happens in the material. In the material there is absorption, right. This is the input or the source, and then I have to detect something, right. Now, in the frequency domain, if I am doing a frequency domain experiment, what I end up detecting, or what I should end up detecting, is something like this. There is nothing at frequency omega naught, this is omega naught, there is nothing there, and then so something above that. Okay. So, this omega naught frequency is gone. So, that I am going to write it as in a different color. So, that is gone. So, there I am detecting nothing, I am detecting 0 actually. Okay. So, that is what I detect in the frequency domain. So, there is no so it suddenly goes to 0 and then goes up, right. So, that is how I should, okay, sorry, let me draw that again. So, okay. So, sorry, let me give it some slope and do this, right. And here let me draw it in a different color. Suddenly I have a 0 intensity. Okay. So, I am just exaggerating that part a bit. Okay. So, this is what I should detect in the frequency domain. This is what the detector sees. What does the detector see in the time domain? The detector sees this minus this, right. So, that will be some sort of a function that goes like this here, right, and there is going to be some function that keeps going like this here, and there is also some function that keeps going like this. Okay. So, this is what I should detect in the time domain. If I have absorption, my absorption is only at a particular frequency. I will have materials where absorption is only at a particular frequency. Absorption is at omega naught, right. Then if I shine an electric field of time t, this is input, output, so this is t equal to 0, is if I am measuring again electric field as a function of time, right. So, in this hypothetical experiment, what I should see is an output which is wavy, that is okay. Here also it is a bit wavy, that is also okay, but I am also seeing it wavy here, right. So, I see some electric field intensity, and this electric field intensity also exists at t less than 0. Oh my god, how does the system know? So even when this means that even before I shine the electric field, the system starts to respond, right. So, I am measuring some input, some output from the system even before I force the system, right. That is unphysical, right. So, even before I could push you, you fall down. So, I am not responsible for you falling down, right. But this analysis that we did, where if the material has a magic absorption frequency omega naught, even before I can apply the impulse, the system is already responding, right. So, this is the response of the system. This is the input, right, and that violates. So, this is unphysical because it is violating causality. Cause and effect, cause should come first, effect should come next, effect should always follow cause, effect should not come before cause. If effect comes before cause, this is violating what is called causality, right. Causality means cause comes first, effect follows, right, but effect should not come first and then cause happens. Here in this case, that is what is happening, right. So, now, right, so it turns out that so somehow the system should adapt to this, right, and this adaptation and trying to follow causality, right, is what relates the imaginary part and the real part of properties, and that I think we will see in the next class. Okay. So, let us end here. So with this thought that so if I have this magic material that absorbs at omega naught, if I just blindly do this analysis that I did, this hypothetical analysis, then I violate causality. I should not be violating causality. Causality is something which is very sacrosanct, right, in physics. So, if I do not violate causality, what is it that I should do, right. So, I should so the fact that system is absorbing at omega naught should be spread out to the other frequencies, and so the other frequencies should be aware of this, right. So, that is what relates the imaginary part with the real part of functions, and that analysis we will do in the next class. Okay. So, until then, goodbye. Thank you very much.